Hello and welcome to this month's webinar from the IEA Clean Coal Centre. My name is Kyle Nichol and I am an analyst and author at the Centre. Our webinars are based on our technical reports which are available from our website www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after a one-off registration. Today's webinar is on the management of coal combustion waste and is presented by my colleague Xing Zhang. Xing's report on this subject should be available on the website early in the new year. If you have any questions to ask Xing, please use the Ask a Question box at the top of your screen. Add your email address as well so that Xing can send you a full answer if we run out of time. So, over to you, Xing.
Thanks, Kyle. Good afternoon and welcome to my webinar. My name is Xing Zhang. Today I'm going to talk to you about my recent study on the management of coal combustion waste. In my presentation today, first of all, I'm going to introduce to you the types of coal combustion products and their characteristics. Then I'm going to talk about the legislation used to regulate the management of coal combustion products and their disposal. I will then summarize the coal combustion product disposal method before finally covering the environmental impact of coal combustion waste disposal. As the organic compounds of coal combust, a variety of solid waste are generated inside the boiler from unburned inorganic components and unburned carbon. These solid wastes are known as coal combustion products, or CCPs. Some CCPs can be beneficially used. For example, fly ash used in cement or concrete production. CCPs that cannot be used will have to be stored or disposed of. They are often referred as coal combustion residues or coal combustion wastes. At the 2013 World Coal Ash Conference, members of the Worldwide Coal Combustion Products Network called for a harmonization of the terminologies of CCPs. How the material is referred to generally depends on the context in which it is being discussed. As my study focuses on CCP disposal, I refer them as coal combustion wastes, or CCWs. This table gives the production of total combustion products and their utilization rate for selected countries from 2009 to 2011. Only around 53% of coal combustion products are utilized. The Worldwide Coal Combustion Products Network estimated that world total production of coal combustion products was approximately 700 million metric tons in 2010. If this estimation is correct, there were about 360 million tons of coal combustion waste which needed to be disposed of in 2010, and this figure would continue, if not increased, for some years. There is a suspicion that the utilization rate has been exaggerated due to pressure from environmental protection groups, as utilizing CCPs could enable power plants to lower their carbon footprint and minimize the effect on the environment. This exaggeration could result in underestimation of environmental impact of CCWs. The type of coal combustion product or coal combustion waste varies depending on the mineral components of coal, the combustion technique, and emission control technologies. This slide lists some of the main types of coal ash. The first three are formed in powerized coal-fired power plants. FBC ash is from fluidized bed combustion boilers. FGD gypsum is from the flue gas desulfurization process. Other FGD residues, such as spray-dry absorption product and ammonia FGD residues, are not listed in this slide. In my report, CCWs are separated into two groups: ashes and pollutant control residues. First, let's discuss ash characteristics. Physical characteristics of coal combustion ash of interest for disposal are particle size and its distribution, compaction behavior, permeability, and shear strength. Typical values for the ashes are listed in the table. Chemical characteristics are strongly influenced by the source and the type of coal and the technique used in its handling and storage. Combustion processes and the operating conditions for boiler also have an effect. Factors influencing ash chemical characteristics are plant and coal specific. The pH of fresh fly ash and the boiler ash generally range between 4.5 and 2. In general, over 90% of ash is made up of silicon, aluminium, iron, and calcium in their oxide form. The ashes are also likely to include a certain level of toxic organic compounds. The characteristics of pollutant control residues differ both physically and chemically from conventional fly ash, mainly because of the reagents used to control pollutants and modifications to the combustion technology. Compared to fly ash's fine texture, the texture of FBC ashes and FGD residues is coarse. Bulk density and the moisture content are higher in FBC ash, as you can see in the table. For chemical characteristics, the calcium and sulfur-based compounds may be predominant due to the chemical-based additives used to capture SO2. Now I'm going to move on to the legislation. To date, there's no specific international law on CCW management. The commonly regarded international agreement is the United Nations Basel Convention. In Europe, most of the countries follow the EU's European Waste Classification for Statistics and then interpret the EU regulations into their own domestic legislation. The foundation for regulating CCW disposal lies on the classification of CCPs. In most countries, CCPs are considered to be non-hazardous solid waste. This may be for the purpose of encouraging the use of coal and avoiding unnecessary regulatory burden on the utility industry. It may also be for the benefit of reusing CCPs. Currently, there is a lively debate in the US, Europe, and South Africa about regulating coal ashes as hazardous waste. At the moment, CCPs are generally classified as non-hazardous waste. It is the addition note, such as if the toxic substance exceeds the limit, that decides whether the CCPs generated from a power plant are hazardous or not. There are 4 principal methods for disposing CCWs. surface impoundment, landfill, mine and quarry fill, and ocean disposal. Mine fields are covered in other IEA Clinical Centers report. The latest report on this topic was written by Dr. Sloss earlier this year. Her webinar about the study is on our website. Ocean disposal is not commonly used today. Therefore, my study only focuses on surface impoundment and landfill. Surface impoundment units are often called wet ponds. The CCWs are mixed with water and pumped as slurry directly from a power plant to the impoundment unit, where solids settle out, leaving relatively clear water at the surface. This water may be recirculated into the plant or discharged. Solids may accumulate until the impoundment unit is full, or the pond may be drained and the solids dredged periodically and taken to another disposal unit, such as a landfill. By using this method, certain types of waste treatment, such as neutralization, can be accomplished concurrently with disposal. Historically, wet ponding has been one of the most widely used disposal methods because it is simple and easy to implement. In recent years, regulations concerning wet ponds have become more restrictive. These include installing liners to prevent leakage and systems to monitor the quality of the groundwater. The structural safety of dams and dikes has become increasingly important too. These types of restrictions will tend to increase wet ponding costs, making it less attractive as a disposal option. CCWs, when they are produced or after they are dredged from surface impoundment, can be disposed into landfills. Dry CCWs are typically loaded on trucks, wetted to prevent dust emission, and then transported to a dedicated landfill facility. Most large landfills are divided into sections or cells, of which only one or two may be active at any given time. A landfill cell is defined as the area in which waste is placed. It has a depth ranging from 0.3 to 3 meters. Industry practice refers to each layer of cells as a lift. Several lifts may be stacked on top of one another in the landfill. A cell may be open for a day or a few weeks, after which it is usually covered with several meters of soil. The waste and the soils are often sprinkled with water throughout the field operation to mitigate potential dust problems. Comparing the two methods, on-site surface impoundment has low delivery costs, but may produce more leachate. It requires large quantities of water and about 2.5 times more land than a comparable landfill site. After the American Kingston ash pond spill, an even more pronounced trend towards dry ash disposal may be expected. Now I will use the New Zealand Huntly coal-fired power plant to demonstrate ash management. The Huntly power station comprises of 4 250 megawatts units. The plant uses ESP to control particulate emissions. No FGD system is fitted, so only fly ash and bottom ash are produced, with 75 to 80% of the total being fly ash. The annual ash production rate varies between 50 to 100,000 tons. The ashes that are not collected by a local cement company are mixed with water into a slurry. This ash slurry is then pumped from the station via a pipeline to 5 ash ponds located 2.5 kilometers to the north of the station. Here, the ash settles out. Decant water from the ponds is pumped back to the station and discharged to the nearby river with the cooling water. The settled ash from the ponds is transported by truck to the Hampton Downs landfill. The two bigger photos in this slide show the layout of the power station. The small picture in the middle shows the schematic of the ash management system. The top photo on the right-hand side shows the pond number, and the bottom one shows the water quality monitoring points surrounding the ash pond. The two small photos in the middle show removal of ash from the ash pond. CCW is generated in large volumes and has been accumulating at some sites for decades. Based on the chemical properties outlined earlier, CCW is likely to contain certain hazardous components that pose a risk to human health and the environment if it is not properly managed and adequate controls are not in place. The main hazards are soil contamination, water contamination, dust dispersion, and toxin entering the food chain. The impact CCW disposal poses to the environment and human health are affected by environmental, population, and ecological characteristics of the disposal sites. Some of these are listed in this slide, and further details can be found in my report. Now I'm going to discuss the potential environmental risks. Water contamination and a sudden release of liquid waste are the two main potential risks associated with the CCW disposal. There's also a danger of ash being blown from the site by the wind. Radioactivity and mercury may come into contact with the general public when they are dispersed in air and water. Of these, water contamination is the primary concern, as hazardous composition in CCW have the potential to leach into the surface or groundwater, and hence pollute drinking water, surface water, or biota. Leaching is a slow and complex process which depends on chemical speciation of the compound, solution pH, availability of the constituent for leaching, and the age of the ash. In addition, subsequent chemical reactions and secondary mineral formation can further modify leaching characteristics. At a CCW disposal site, the environmental impact of leaching may be affected by the size of the disposal pond, the pond depth, and the amount of pressure the waste creates. The underlying geology and the gradient or slope of the land also affect leaching, and the distance of an aquifer or underground stream beneath the pond or the landfill might influence leaching as well. Since the year 2000, the US EPA has been identifying the damage cases caused by CCW leaching. Up to 2011, over 100 damage cases in America has been identified. Although not investigated as comprehensively as in the US, other countries such as India and China have also made considerable efforts in reporting CCW's leaching impact on the environment. The ash pond in this slide belongs to the China Tangshan Douhe power plant. It has a capacity of 68 million cubic meters and was built without any liners. As a consequence, the nitrate concentration in its underground water was 36% higher than the standard for drinking water. Leaching can be controlled by the use of liners, leachate collection systems, diversion ditches, caps, and vegetation. Monitoring networks are used to ensure the performance of the engineering controls in protecting groundwater and surface water resources. I'll go through these practices in a bit more detail. Most countries require the installation of a liner system for new ash disposal sites. Liners are also being retrofitted at old sites. Liners can consist of compacted soil, compacted clay, a synthetic material or membrane, or a combination of these barrier types. There are single liner system and a composite liner system. Details on each liner system and its advantages and disadvantages can be found in my report. The picture in this slide is a conceptual layout of a new composite liner system introduced by Zimmer and colleagues this year at the World Coal Ash Conference. A leachate collection system is a series of drains placed beneath a disposal unit. Groundwater monitoring systems consist of one or several wells drilled around a disposal unit. In China, it is suggested to establish at least 3 water quality monitoring wells near the coal ash storage and handling facilities. In the previous slide of Huntley Power Station, there are at least 6 for Pond 5. Facilities employed a variety of waste treatment processes to alter the physical and chemical characteristics of the waste to make sure they are compatible with the disposal method. Generally, the pretreatment method includes sludge dewatering, reagent addition, and low-volume waste treatment. Surface impoundment ponds hold liquid waste that has been sluiced from power plant. Wastes are generally held within the pond by depositing it in a nature or man-made depression in the ground or through the use of an earthen dike. If part of pond is breached, then the liquid coal combustion waste will be released into the environment. The most dramatic example of a sudden release is the December 2008 spill at the U.S. Kingston coal-fired power plant. The retaining wall of its 50,000 square meters ash pond had a structure rupture, which released about 4 million cubic meters of wet coal ash. The top 2 photos show the before and after Kingston ash pond release. The bottom 2 photos show before and after the cleanup. After the Kingston release, the U.S. EPA declared its intention to tighten the CCW regulations. All disposal units are required to have some type of permit to operate. New surface impoundments are likely regulated under provisions of the state's dam safety program to address the structural integrity and under the terms of a wastewater discharge permit program. A large proportion of CCWs are fine materials that can become airborne if they are allowed to dry and are exposed to windy conditions. This photo shows a coal ash dust storm that occurred on the 16th of March 2010 in Gansu province in China. Mercury emissions from CCWs in landfills or surface impoundment is expected to be small because of the low temperature involved and the existence of a relatively small surface area per unit volume of residue. Since the residues are typically alkaline and the mercury is absorbed on alkaline particles, the leaching potential is also expected to be minimal. Although the radionuclides are enriched in the fly ash, in comparison to the coal itself, the average radionuclide concentrations in ash are within the range of concentrations found in other geologic materials such as granite and shale. Research by the US EPA, Australian Ash Development Association and others have shown that fly ash is not radioactive and does not represent a significant health risk. To sum up, while coal remains a major fuel for energy generation, large amount of coal combustion waste will be generated which require disposal. CCW disposal and its environmental impacts are influenced by its characteristics, which in turn are influenced by coal source and its quality. Coal combustion process, coal-fired materials, air emission control methods, degree of ash weathering, and so on. CCW is generally managed in two ways, landfills or surface impoundment. More than half of the coal-fired power plants manage their CCW on-site, mostly using surface impoundment. Landfills are commonly used off-site. On-site surface impoundment has low delivery costs but require a large amount of water and more land than landfill disposal. It also has a bigger potential for generating leachate. After the catastrophic ash spill from the US Kingston power plant, more attention has been put into dry ash landfills. The primary environmental concern for CCW disposal is leaching, which may contaminate surface and groundwater. The seriousness of the environmental impacts from leaching is still being debated. To prevent potential environmental risks posed by leaching, liner leachate collection systems, groundwater monitoring system, or pretreatment technologies should be employed. The structural integrity of surface impoundment has become more important after the Kingston ash plant failure. Fine ash can become airborne under windy conditions. However, little has been published about the environmental effects of dust generated at CCW disposal sites. No significant health risks from radioactivity and mercury has been reported. Whilst the decision on whether CCPs are hazardous or not is important, for CCW management, the impact is not as big as for CCP utilization because the liner requirements for hazardous or no hazardous waste are identical. from a technical perspective, both classifications demand the same technologies in preventing leaching. Over the last decade, a number of changes have occurred globally in the coal-fired power generation sector that have affected quality and the quantity of CCPs. The regulations for CCW management, which are currently under discussion, will also have an impact on the cost of CCW disposal. While continuing searching for safe and beneficial pathways for CCPs, CCW management is facing new challenges. Thank you for listening.
Thank you very much, Xing, for the interesting webinar. And now to move on to some questions. So, the first question is, you mentioned that the utilisation rate of coal combustion products was exaggerated. How?
In my report, I used China as an example to discuss this. The Chinese government set up a goal in their 5-year plan for 2006 to 2010 to utilize 60% of solid industrial waste. It's stated in the plan that the rate of coal ash comprehensive utilization should reach 75%. However, research has shown that the real utilization rate is far below this. I think one of the reasons for low utilization rate is that it is coal users' responsibility to utilize the ashes. Although power sectors must submit their data to the governing bodies, it is not clear who is in charge of verifying the data.
Thanks again. We've got quite a few questions to get through, so I'll move on. The second question is, does co-firing have any impact on the ash chemical characteristics and the management of coal combustion wastes?
Co-firing can alter the chemical composition of the resultant ashes. For example, some biomass fuels have a high silicon content, for example, rice husk, and some have a high alkaline metal content, for example, wood. Pet coke has a high nickel level. Therefore, co-firing coal with pet coke may enrich this specific component. Because the chemical composition has been changed, the mobility of metals will change. Consequently, the leaching behavior will change. This will impact the CCW management.
The next question is, what factors should be considered when designing a wet ash pond?
Factors like local condition, the relevant regulations, and whether the CCWs are to be treated in the pond should be considered. More details are in my report. Due to the time limit, can I have your email address, please, so we can discuss these questions via email?
So moving on to the fourth question, who is driving international regulation on CCW disposal? Is it the environmental NGOs or national governments?
I think it's the interest from all parties. especially after the U.S. Kingston ash pond spill, more attention has been driven into regulate CCW disposal. And as I mentioned before, at the moment there isn't international regulations on this, so all the parties are calling for a clear regulation.
Moving on to the fifth question. Have there been any studies on the long-term health effects of CCW landfills on local populations?
I believe there is. I covered a little bit of this in my report, but when I did my study, I did see some papers on health effect of CCW landfills. If you give me your email address, I will try to find the papers and forward it to you.
Moving on to the sixth question. Is there any good way to quantify the pollutants from coal combustion, such as the kind of pollutants, the rate of pollutants generation? That's quite a complex question. However, I'll leave Xing to answer it to her best.
Is there any good way to quantify pollutant from?
Email.
Again, can I discuss with you via email? There are lots of studies has been carried out in this topic. I did see quite a few papers. I would like to discuss with you through email.
Here's a good question. Is there any experience with wet CFB ash ponds? There might be problems because of the lime content.
I'm not quite sure about this. Again, I think I need to find out this and email to you.
Okay, I think that's it. We've had 7 questions so far. There's no more come through just yet. Okay, in the meantime, next month's webinar will be presented by our General Manager, Dr. Andrew Michener. His research subject is the challenges and opportunities for coal gasification in developing countries, and it will take place on Wednesday the 8th of January, midday UK time. Finally, there's no more questions, so thanks to the listeners for the questions, and thanks to Xing for your answers. The PowerPoint presentation will be available to download from the webinar page of our website later. And thank you very much. Goodbye.